Welcome to Module 2, Monitoring Drought. From early warning to impact-based forecasting, part of the course getting ahead of drought. Innovative risk monitoring and financing options. Building on what we covered in Module 1, this module turns to how drought is tracked, forecast, and turned into a trigger for early action. This module provides details on drought monitoring mechanisms, including the early warning system and key indicators for drought identification and declaration. By the end of this module, you should be able to achieve the following objectives. First, understand the role of drought monitoring systems and early warning systems in detecting emerging drought conditions. Second, become familiar with key drought indicators used to identify and monitor drought development across climatic, agricultural, and hydrological systems. Third, explore major data sources and tools, including remote sensing, climate forecasts, and satellite-based monitoring platforms used for impact-based drought forecasting. And fourth, understand how evidence-based trigger thresholds are established to link forecasts and impact projections with early actions and prearranged financing mechanisms. We begin with Section 2.1, Monitoring Drought Risk. Droughts can adversely impact agriculture, food security, hydropower, industry, health, livelihoods, personal safety, and access to education. The specific effects vary based on the socioeconomic context of the drought, so the impacts relevant to a specific drought monitoring and early warning system are key factors in choosing appropriate drought indicators. A drought impact is an observable loss or change that occurs at a specific time due to drought. Drought risk management involves hazards, exposure, vulnerability, and impact assessment, a drought early warning system or DEWS, and preparedness and mitigation, according to WMO, UNCCD, and FAO. 2013. It is important that drought indicators or indices accurately reflect the impacts experienced during droughts. As droughts evolve, the impacts can vary by region and by season. This module discusses the key components of the drought monitoring system, the drought early warning system, and key indicators for drought monitoring. Droughts are a normal part of the climate pattern and can occur in any type of climate worldwide, including deserts and rainforests. They are among the costlier natural hazards on a year-to-year basis. Their impacts are widespread and significant, affecting many economic sectors and people at any given time. Drought has widespread impacts on agriculture, water supply, energy, and ecosystems. Effective monitoring helps track onset, severity, and duration, support timely decision-making, reduce losses through early action, and improve planning for water and food security. Without monitoring, drought response is often reactive rather than proactive. Drought monitoring systems are integrated systems and platforms that collect, analyze, and interpret data to assess drought conditions. The key components of a drought monitoring system include climate data such as rainfall and temperature, hydrological data including river flow and groundwater, soil moisture and vegetation conditions, and remote sensing and satellite observations. These systems generate drought indices such as the Standardized Precipitation Index, SPI, the Normalized Difference Vegetation Index, NDVI, and soil moisture anomalies. The Drought Early Warning System aims to track, assess, and deliver information on climatic, hydrologic, and water supply conditions and trends. Ideally, it has both a monitoring component and a forecasting component. Its main objective is to provide timely information in advance of, or during, the early onset of drought, to prompt action within a drought risk management plan and reduce potential impacts, according to WMO and GWP. 2016. An early warning system has 4 components. Risk knowledge, identifying drought-prone areas, vulnerable populations, and sectors such as agriculture, water supply, and livestock that are most susceptible to drought impacts. Warning service, tracking rainfall, soil moisture, vegetation health, stream flow, and reservoir levels to detect drought conditions and provide timely forecasts and alerts. Dissemination, communicating drought forecasts, warnings, and advisory information to farmers, water managers, communities, and decision-makers through accessible and timely channels. And response capability, enabling communities and institutions to take early actions, such as water conservation, drought-resilient farming practices, contingency planning, and resource mobilization to reduce drought impacts. Drought early warning systems help detect early signs of water stress and rainfall deficits. They support seasonal forecasting and outlooks, triggering anticipatory actions such as water conservation or crop adjustment, informing government policies and relief planning, and reducing impacts on vulnerable communities. In short, early warning systems shift the focus from crisis response to risk management. Let's move to Section 2.2, Indicators and Integrated Monitoring. Since various sectors are affected by drought in different ways, no single indicator or index can reliably determine the best actions for all types. The optimal method involves applying different thresholds with various input combinations, ideally established through prior research to identify the most suitable indicators or indices for specific timing, regions, and drought types. Relying on quantitative index-based assessments is crucial for accurately evaluating drought severity and providing the necessary input for an operational drought early warning system or a comprehensive drought management plan. There are three main methods for monitoring drought and guiding early warning and assessment. Using a single indicator or index, an older method used when there are limited data against the available indicators. Using multiple indicators or indices, a tried and tested approach for drought assessment, and using composite or hybrid indicator, which enhances drought severity evaluation by incorporating multiple water availability indicators for a specific area. Drought is estimated with a set of indicators and indices, so it's important to understand these concepts. Indicators are variables or parameters used to describe drought conditions. Examples include precipitation, temperature, stream flow, groundwater and reservoir levels, soil moisture, and snowpack. Indices are numerical representations of drought severity, derived from climatic or hydrometeorological inputs, including the indicators just mentioned. They aim to measure the qualitative state of drought on the landscape for a given time period. A few commonly used indicators and indices for drought assessment: the Standardized Precipitation Index, SPI, for rainfall anomalies, the Normalized Difference Vegetation Index, NDVI, for vegetation health, soil moisture indices for agricultural stress, the Palmer Drought Severity Index, PDSI, for long-term drought assessment, and the Standardized Streamflow Index, SSI, to measure river discharge or streamflow data. For more information on drought indicators and indices, refer to the Handbook of Drought Indicators and Indices by the World Meteorological Organization and Global Water Partnership. India has developed a multidimensional drought monitoring system that combines meteorological, agricultural, and remote sensing indicators to support timely drought assessment and response. Key institutions: the India Meteorological Department provides rainfall and temperature data. The Ministry of Agriculture and Farmers' Welfare leads agricultural monitoring and advisories, and the National Remote Sensing Center supports satellite-based drought assessment. Key features of the system: rainfall monitoring using district-level deviations and the Standardized Precipitation Index, vegetation health monitoring using NDVI from satellite data, soil moisture assessment and crop condition tracking, and weekly and seasonal drought outlooks at national and state levels. India uses composite drought indices that combine rainfall, vegetation, and soil moisture conditions to provide a more realistic picture of drought severity. How the system supports action: it enables early identification of drought-prone districts, guides state governments in declaring drought conditions, supports crop advisories and contingency planning, and informs the allocation of relief funds and water management measures. During deficient monsoon years, integrated indicators help distinguish between meteorological drought and actual agricultural stress, ensuring targeted interventions rather than blanket declarations. Key lessons: integration of multiple data sources improves reliability. Satellite data is critical for real-time monitoring at scale. Institutional coordination is essential for translating data into action, and linking monitoring with clear response triggers strengthens early warning systems. Key outcomes: improved accuracy in drought assessment, reduced delays in response and relief measures, and better coordination between national and state agencies. This diagram illustrates satellite monitoring of agricultural drought, showing how meteorological drought, rainfall and infiltration into the soil, cascades into agricultural and hydrological drought, tracked through evapotranspiration, biophysical parameters, and vegetation indices captured by satellite sensors. Source: NRSC ISRO. Let's look at a few commonly used indices for drought assessment, drawing on work from India's National Remote Sensing Center. The LSWI index is a plant moisture-based index using near-infrared and short-wave infrared bands. It has no saturation issues and is sensitive to surface wetness during the sowing period. The NDVI index is a robust, chlorophyll-based index reflecting plant vigor and density, with easy computation and interpretation. And combining NDVI and LSWI overcomes the limitations of either index alone. It amplifies anomalies and is more responsive to the actual ground situation. Source: NRSC ISRO. Drought evolves through connected stages: rainfall deficit, soil moisture stress, vegetation stress, and water supply stress. First, meteorological indicators: rainfall anomaly, temperature, SPI, and SBI, capture the initial rainfall deficit. Rainfall deficit alone may overstate or understate impacts where irrigation, groundwater access, or reservoir storage buffers the shock. Second, hydrological indicators: river flow, reservoir storage, groundwater and agricultural indicators, soil moisture, NDVI and FAPAR, evapotranspiration, track how that deficit propagates. Hydrological drought normally appears later than meteorological drought, so monitoring must track both current stress and emerging risk. Third, these streams feed into an integrated drought situation assessment. And fourth, this assessment produces early warning products, situation bulletins, advisory or trigger information, hotspot maps, and seasonal outlooks. Integrated assessment reduces false alarms and helps target response before impacts become severe. The key message here: no single indicator can capture drought onset, severity, persistence, and impacts on its own. Let's look at how 3 real-world operational platforms put this into practice. The Copernicus European and Global Drought Observatory combines precipitation, soil moisture, and greenness vegetation anomalies. It produces watch, warning, alert, and recovery classes, and is useful for agricultural drought early warning and hotspot tracking. Its typical output is a drought status map, along with graphs and time series. India's NADMS and drought manual practice uses rainfall, satellite indices, soil moisture, sowing progress, and irrigation statistics. It issues normal, watch, and alert classifications from June to August, and mild, moderate, and severe assessments from September to October. It supports state drought declaration and agricultural contingency planning, and reported an average matching of state declarations and NADMS assessments across 14 states from 2012 to 2015 of 76%. The U.S. Drought Monitor and Drought.gov produce a weekly national drought map using physical indicators and field input, classifying drought from D0, abnormally dry, to D4, exceptional drought. It draws on precipitation, temperature, soil moisture, stream and lake levels, snow conditions, and observed impacts, with a typical output of a weekly map and change statistics. Across all 3, there's a common operating pattern: multi-source data, expert and field validation, regular updates, and decision-oriented outputs. So what makes an early warning system effective? 4 things: cross-sector coordination, clear thresholds and triggers, regular updates with local validation, and communication that is timely and actionable. This plays out across 5 stages: observe rainfall, stream flow, reservoir levels, soil moisture, and vegetation, asking what is happening; analyze anomalies, trends, thresholds, and composite indices, Asking where is risk highest. Assess hotspots, severity class, likely impacts, and confidence level. Asking how might conditions evolve. Communicate bulletins, dashboards, maps, seasonal outlooks, and advisories. Asking what action is required. And act. Crop advice, irrigation scheduling, water allocation, and anticipatory action. A good early warning system does not stop at monitoring. It connects information to decisions, response triggers, and early action. The key outputs from this stage are the situation bulletin, the hotspot map, the seasonal outlook, and the response trigger. This brings us to section 2.3, from risk information to early action. There are 4 complementary windows onto the same problem. No single source tells the whole story. Remote sensing. Satellites track vegetation greenness, plant temperature, and moisture from space. Flagging crop stress, even where there are no ground stations. Seasonal climate forecasts. Outlooks on rainfall and phenomena like El Niño give a heads up of weeks to months, hinting at whether a season is likely to run dry. Satellite monitoring platforms. Operational online platforms turn raw satellite data into ready-to-use maps and alerts, refreshed regularly through the growing season. And national monitoring frameworks. Countries combine rainfall, soil moisture, and river flow indices into one homegrown system suited to their own climate and crops. Here are a few widely used, publicly documented tools, chosen for ease of use and a proven track record. The Vegetation Health Index, or VHI, is a satellite and remote sensing source that flags crop and pasture stress from space, weekly, almost anywhere on Earth. The Standardized Precipitation Index, SPI, is a national monitoring framework, WMO's recommended starting point for rainfall-based drought monitoring. The Agricultural Stress Index System, ASAS, is a satellite monitoring platform that produces ready-made drought category maps every 10 days at high resolution. The El Niño/ENSO Outlook is a seasonal climate forecast, a monthly updated probability that a wetter or drier season is coming months ahead. And the Regional or National Drought Monitor is a national composite framework that blends dozens of indicators into one weekly, easy-to-communicate severity map. Early warning key information should answer 6 questions. What is the event or hazard being anticipated? Which area is it going to hit? How soon is it coming? How bad will it be? How sure are the experts? And what should people do? For anticipatory action, a trigger should be defined to confirm when and where to intervene and access financing for implementing those actions. The more precise the forecast is, the more confident the anticipatory action trigger decision is, and the better the early warning information. Source: Anticipation Hub. This diagram brings the pieces together. Risk knowledge and monitoring and warning feed a harmonized anticipatory action plan built around thresholds. Once a threshold is reached, pre-agreed sectoral early warnings, in-kind support, and cash distribution are triggered, supported by readiness activities and prearranged funding mechanisms along the way. Source: Anticipation Hub. The terms early action and anticipatory action are closely related and sometimes used interchangeably, but there are important differences in concept, timing, and operationalization. In drought management, this distinction is particularly relevant because drought is a slow onset hazard with long lead times. On definition, early action means actions taken early to reduce disaster impacts once a risk becomes apparent, while anticipatory action means pre-agreed actions implemented before a hazard hits, based on forecast triggers and predefined plans. On trigger, early action can be based on early warning information, observations, or expert judgment, while anticipatory action is triggered by scientifically defined forecast thresholds agreed in advance. On planning, early action may be planned or decided during an event, while anticipatory action is fully pre-planned, with predefined actions, responsibilities, financing, and triggers. On financing, early action funding is often mobilized after warnings are issued, while anticipatory action financing is arranged in advance and automatically released when triggers are met. On decision-making, Early action is more flexible and sometimes reactive, while anticipatory action is rule-based and protocol-driven. And on objective, early action aims to reduce impacts by acting earlier than traditional response, while anticipatory action aims to prevent or minimize impacts before they occur through forecast-based action. Anticipatory action sits between seasonal preparedness and formal disaster response, activated as forecasts signal a rising risk ahead of peak shock, and it works to reduce impacts before they escalate. Response then follows to address impacts directly, moving into recovery, with long-term resilience building and climate change adaptation running underneath the whole cycle. Source: adapted from the ASEAN Framework on Anticipatory Action in Disaster Management. It helps to contrast anticipatory action with traditional response directly. Anticipatory action moves before the hazard strikes. Forecasts trigger pre-agreed support so households and systems are better prepared when the shock arrives. Traditional response, by contrast, moves after the hazard has already caused damage, mobilizing aid once the emergency is visible on the ground. Source: adapted from OCHA Anticipatory Action Toolkit. Developing an anticipatory action trigger follows a sequence of steps. Step 0 is a feasibility assessment, confirming that the hazard is predictable, suitable forecasts are available, and early actions can be implemented within the available lead time. Step 1 is reviewing historical impacts, analyzing past hazard events, losses, affected populations, and severity levels to understand when impacts become significant. Step 2 is selecting the forecast and lead time, identifying the most reliable forecast source and the lead time that provides sufficient accuracy and time to act. Step 3 is defining the geographic target, determining whether activation will cover specific communities, districts, river basins, or a wider administrative area. Step 4 is setting the activation threshold, establishing the forecast probability, hazard magnitude, or expected impact level that will trigger anticipatory action. And Step 5 is clarifying decision-making and coordination, defining who validates the trigger, authorizes activation, communicates decisions, and coordinates implementation. In practice, drought triggers are built by layering signals over time, from months ahead down to the decision point. Step 1: months ahead. The seasonal and ENSO outlook flags the possibility of a dry season early. For example, in Kenya, poor seasonal rainfall outlooks help planners prepare before the main rains begin. Step 2: satellite vegetation data checks whether crops, pasture, and vegetation are beginning to show stress. For example, declining vegetation condition indicators show where drought stress is emerging on the ground. Step 3: closer to real time. The National Monitoring Platform confirms the official drought status using regularly updated national data. For example, districts are classified by drought severity to guide local government action. And Step 4: at the decision point, analysts bring the combined assessment together, comparing all signals before deciding whether to trigger early action. For example, if forecasts show rainfall deficits, satellite data confirms vegetation stress, and the National Drought Monitor shows worsening conditions, early actions such as cash support, fodder, water trucking, or seed distribution can be activated. Laid out across a timeline, this looks like: months ahead, the seasonal and ENSO outlook raises early awareness that a season may run drier than normal. Weeks ahead, satellite vegetation data confirms whether crops and pasture are actually showing stress on the ground. In real time, the National Monitoring Platform produces the official drought category map that local decision-makers trust. And at the decision point, the combined assessment brings analysts to weigh all three together before recommending action. We now move to Section 2.4, Triggers, Financing and Application. An evidence-based trigger takes the guesswork out of drought response. It defines exactly how severe the impact is expected to be, how likely that scenario actually is to occur, and how much time remains to act before the damage is done. Setting a good threshold means asking, what did past droughts actually do to crops, herds, and household food security in this area? At what index value or forecast probability did serious damage historically begin? How far in advance can we detect that level reliably? And is there still time left to act? And do we need different thresholds for entering a drought versus recovering from one? This plays out along a critical timeline. Watch. The forecast shows rising odds of a dry season, and preparedness resources are checked and ready. Pre-alert. Ground indicators confirm early stress before planting or during a sensitive crop stage. An alert or trigger reached. The threshold is crossed, and pre-agreed early actions and financing are released automatically. The goal is to make money and action move the moment the threshold is crossed, not after a formal disaster or drought is declared. Forecast probability uses climate and seasonal forecasts to estimate the likelihood of drought before impacts occur, providing advance notice when conditions indicate an increased risk of rainfall deficits or prolonged dry spells. For example, a greater than 55% chance of a drought-inducing El Niño, or a rising probability of crop-level water stress. Projected impact converts forecast information into likely consequences for people, livelihoods, and the economy, highlighting who and what will be affected, the severity of expected losses, and where interventions are most needed. This is translated into concrete terms: expected yield loss, number of households likely to be food insecure, and herds at risk, and pre-agreed early action and financing. Defines a set of agreed actions and dedicated funding that are activated immediately when forecast thresholds are reached, enabling timely support to vulnerable communities before drought impacts escalate. Seeds, fodder, cash transfers, or irrigation support released automatically once the threshold is met. Let's turn to a case study from Papua New Guinea. When the alarm rings too late. Papua New Guinea is one of the most drought-exposed countries in the Pacific. Over 80% of people farm for subsistence, and more than 60% rely on sweet potato as their main food. The 2015 to 2016 El Niño drought cut highland sweet potato yields by up to 50%, drove a 75% price spike, and left 480,000 people in acute food shortage nationally. PNG's early warning system already combined a 3-month rainfall index, SPI3, a vegetation index, VHI3, and a seasonal outlook. But its thresholds, SPI3 below -1, VHI3 below 40, only fired once a drought had already taken hold, leaving little real time to act before impact. Looking at the old signal on a timeline, almost no lead time separated the droughts unseen beginning from the point yields actually fell. The old system's signal confirmed a drought already underway, not one that was coming. The gap this case study closes is a genuinely predictive combination of indices, not just a faster confirmation. FAO and the PNG National Weather Service built a combined drought index, or CDI, that follows the real cause and effect chain of drought, with a forecast layer added purely for lead time. The chain runs through 4 signals. First, rainfall deficit, captured by SPI1, a 1-month rainfall index. Second, soil moisture drop, captured by SMOPI, a root zone soil moisture anomaly. Third, vegetation stress, captured by VHI, the monthly vegetation health index. And fourth, yield decline. The outcome the chain is designed to catch early. Plus, a bias-corrected 3-month rainfall forecast, SPI3, corrected against 30 years of station data with a machine learning model and informed by El Niño, UNESO, and the Indian Ocean Dipole, IOD. This is what gives the system its lead time. The index was piloted in Western Province, Kiunga District, and Western Highlands Province, and tested against 30 years, 1993 to 2023, of national yield data. The CDI's first real test came with the 2023 El Niño, and it worked as designed. In Week 1, October 2023, the CDI flagged moderate drought in the Western Province, Kiunga District. In Week 2, October 2023, field verification confirmed the signal against local observations and farmer consultations. From October to December 2023, Phase 1 anticipatory action was activated, Water storage, climate-adapted seeds, and livestock feed kits were delivered. And from January to March 2024, the season's worst drought risk period, support was already in place. What the record shows: a hike skills score of 0.99 for correctly forecasting no drought conditions, a skill score range of 0.48 to 0.63 for correctly flagging moderate drought, agreement with ground conditions of more than 90% in the 1997, 2015, and 2023 drought years tested, and real lead time delivered of 2 to 3 months, enough to act before yields fell. What is often called FAO's Anticipatory Action Fund is formally the Anticipatory Action Window of FAO's Special Fund for Emergency and Resilience Activities, SFERA, established in 2004. Its purpose is narrow and specific: to let FAO act early once an impending threat to agriculture or food security is identified, before losses to livelihoods are actually sustained. It sits alongside other SFERA components, a working capital component that advances funds once a donor commitment is secured, and the Agricultural Inputs Response Capacity (ARC) window. Germany's Federal Foreign Office has been a long-running strategic partner, funding it through a recurring 3-year framework agreement. The trigger combines quantitative thresholds, climate forecasts, food security projections, remote sensing data, with qualitative information gathered from the ground, following the same crisis timeline logic covered earlier in this course. A defining feature is that funds can be committed on a no-regrets basis before a detailed needs assessment or response plan is finished, so the clock does not wait on paperwork once a threat is identified. Typical activities are timed to the agricultural calendar rather than to a disaster's aftermath: seed distribution ahead of planting, livestock vaccination and feed support, and small-scale protection of productive infrastructure. Let's look at how this mechanism has scaled. For $0.1 million funded the Anticipatory Action Window in 2020 across 10 countries and 1 subregion, more than triple its 2019 budget. $70 million is requested for global services, including anticipatory action, in FAO's 2026 Global Emergency and Resilience Appeal, and $521.6 million of that same 2026 appeal is earmarked for Asia and the Pacific alone, to assist 30.5 million people. This brings us to the end of Module 2. We've covered why drought monitoring matters, the components of drought monitoring and early warning systems, the indicators and indices used to track drought, how integrated monitoring feeds into early warning and anticipatory action, and how forecasts are turned into evidence-based triggers linked to prearranged financing. Thank you for your attention.